Hello everyone. Today we start a new subsection of p-n junction discussion, which is focused on current voltage characteristic of a p-n junction. And our plan will be the following. So first we will try to understand from qualitative point of view what is going on in a p-n junction in terms of charge transport and energy alignment when we apply forward bias. So that let's consider first forward bias. So what is going on? So we already know quite many things how p-n junction respond to bias, but that is in terms of thickness of the depletion region and geometric capacitance, like depletion layer capacitance, which also changes with applied bias. However, now we need to talk more about this change of potential barriers for diffusion of majority charge carriers and how this changes from equilibrium condition to condition when we apply some bias. So this is a p-n junction energy diagram and some schematic representation. You have seen this already. And we were talking that about this case of thermal equilibrium, that under thermal equilibrium this Fermi energy is the same for all points along the p-n junction. And as a result, because of initial diffusion of majority charge carriers, means electrons from n-type and holes from p-type in opposite directions. So these are diffusion of electrons and diffusion of holes as majority charge carriers. They start to penetrate into opposite regions, and they left behind uncompensated positively charged donor centers and negatively charged acceptor centers. So these guys form internal electric field, and this internal electric field results in potential electrostatic potential distribution. That's what we see here for this band bending. It's actually like mirrored image of electrostatic potential because of negative electric charge. So that's what we have, and under thermal equilibrium, when Fermi energy level is flat, drift current of electrons and holes as majority charge carriers is compensated by, diffusion current of electrons and holes is compensated by drift of electrons and holes from p and n type respectively. So means as minority charge carriers, electric field which is built inside the p-n junction facilitates drift of these minority charge carriers. These currents compensate each other, and eventually the net current in such system is equal to 0. So that is equilibrium condition, and now we will show this energy diagram in a bit simplified way in order to make it easier for graphical representation. So instead of this quadratic band bending, like shape of band bending electrostatic potential, we consider just linear, so as shown here. It just makes much easier to show and explain things. But this particular case actually can be real. So such band bending could be real, and maybe someone has an idea under which conditions we would have such an energy profile for. This? Yeah, this one, in the right side. So this is, maybe it will tell you something. That's a so-called PIN junction, or metal intrinsic semiconductor metal junction. So what is the reason for this quadratic dependence of band bending in regular p-n junction? So in terms of, there is a relationship between band bending, like with potential, electrostatic potential distribution, so that also quadratic function of position. And what is the reason for quadratic electrostatic potential distribution? Obviously there is some electric field which linearly changes in the depletion layer of the p-n junction. We have linear distribution, so we have uniform step function distribution of space charge in the depletion region of p-n junction. Then we integrate it in order to get the electric field distribution. And if we integrate some constant, we get linear function of position x. So that's why we have electric field as a linear function. And then we integrate once more to get electrostatic potential distribution. So that gives us this quadratic function. However, if our electric field inside the semiconductor material is uniform, is constant, means we don't have space charges inside the p-n junction. That's this intrinsic semiconductor when we don't have depletion, like we don't have space charges there. Then electric field is uniform. If we integrate in order to get distribution of electrostatic potential, we end up with linear distribution of electrostatic potential. And that's one is here. So that's quite a realistic energy diagram, quite common for such solar cells as organic and perovskite solar cells, because they usually use this metal intrinsic semiconductor, metal device architecture, which is working because we have different work functions of metals, and then because of this difference in work functions, it creates band bending. But band bending looks like this image in the right side of the slide because we have uniform electric field inside. So that's just some comment on different options for energy diagrams based on conditions of which we use for making devices. So now we take a look on this energy diagram, and we remember it's at zero bias, so there is no external bias. So what do you think will happen when we have forward bias? So first of all, remind me please, what will be forward bias? Which polarity for this case will be forward bias?
When you have negative.
So should be very easy for you guys, because you have space charge here and here formed by positive and negative charges. So internal electric field goes from n-type to p-type. If we want to make a forward bias, we need to be sure that external electric field is in opposite direction. So external electric field is opposite direction. When this will be in opposite direction? So we attach minus to n-type and plus to p-type. So that's, I believe, very straightforward way to consider which polarity will be the forward or reverse polarity for given p-n junction. So what happens? Now you can see that depletion layer became thinner. That's expected. We know that already. And now we want to see at this forward bias, means the potential difference between terminals is considered as positive. We want to see what is going on with the band bending, like bend diagram of this p-n junction, and how this impacts the magnitudes of drift and diffusion currents. So now we apply some negative potential here to n-type semiconductor. If we apply negative potential and energy diagram is drawn with respect to potential energy of electron, that means that this part, like right part of the band diagram, is lifted up. You see that it was here and now it is higher. So we increase potential energy of electrons in the right side of the p-n junction, in particular in this n-type region, and that creates this reduction of the potential barrier. So if you look now here, we have this is our QVBI, height of the potential barrier for majority electrons to diffuse into p-type region. The same height of the potential barrier stands for holes which want to diffuse from p to n region. Now, because of external bias, this potential difference will be Q times VBI minus V. So we reduce the height of the potential barrier, and if we reduce this height of potential barrier, we cause much larger diffusion current, which is marked here with this bold arrow, which flows through this p-n junction. So diffusion current of electrons and obviously holes, because we simultaneously change, reduce potential barriers for them, increases dramatically. It increases according to exponential function that we will show a bit later when we discuss quantitatively the current voltage characteristic. Now we need to understand what's going on there. So at the same time, drift of electrons and holes doesn't change much. So electric field is reduced, so it's less favorable for charge transport with drift mechanism for minority charge carriers, but the current was so small there, like drift current, even with stronger electric field, that it just slightly decreases, but it doesn't make a big difference, so we can consider them as constant. Why the reason is for that, because in the dark, minority charge carrier concentration is very small. So it remains very small, much smaller than the majority charge carrier concentration, and a small change in electric field due to a reduction of electric field within the depletion region because of applied external bias does not make a big difference on this current. So now what we have just increased dramatically diffusion of electrons and holes from N and P type regions respectively. So we can consider this process from different angle. We can consider it as the injection of minority charge carriers, electrons in the P type and holes in the N type in large quantities. So if we inject charge carriers, means we are out of equilibrium condition. So far, when we had no bias, we had one single flat Fermi energy level, which corresponds to thermal equilibrium for all systems. Now we start to inject a lot of charge carriers, in minority charge carriers in opposite regions, and obviously it's not equilibrium condition. So we need to deal with so-called Quasi-Fermi energy levels. So now we need to understand how this profile looks for Quasi-Fermi energy levels. So we had this kind of, in the neutral region, this Fermi energy remains as it was before in terms of, with respect to the top of the valence band and bottom of the conduction band. So the same as here. The shift between them, or in other words, the shift between the splitting between Quasi-Fermi levels in the p-n junction, that will be equal to Q times V applied bias. That happens because we lifted up this right side of the band diagram because of applying negative potential. So we increase potential energy of electrons. These guys going up by distance, which is Q times V. So that always makes sense when you want to see the degree, like quantify some parameter which pushes semiconductor or p-n junction out of equilibrium condition. You always want to look at the splitting between Quasi-Fermi levels, because the more they are splitted, the larger this disturbance. In this case, disturbance is external bias, and that's why we can quantify this splitting of Quasi-Fermi levels by considering Q times V. So now, what is the most important here? What happens in this region? Let me get rid of these parts. So what is happening starting from the point which is the edge of the p-n junction of the depletion region in p-type up to here, and from point here at the edge of the depletion region in n-type semiconductor up to here. So we inject minority charge carriers in this region, like here. Electrons are injected here, and that's why just right on the interface the concentration of minority charge carriers is quite high, is determined by this Quasi-Fermi energy level. However, as they move further inside the neutral region of the semiconductor, like of this p-type semiconductor, so this is this one, this neutral region, their concentration reduces because it is compensated by majority charge carriers electrons, which are plenty of them in the p-n junction, in the p-type region. So this fact is shown by the reduction of Quasi-Fermi energy position up to thermal equilibrium Fermi energy in the neutral region of the n-type p-type semiconductor. So it reduces. So here next to the edge of the p-n junction in this region we have some excessive minority charge carriers, and they start to reduce because of compensation and recombining with majority charge carriers, which are holes. The same happens for electrons, which are injected. So, sorry, not electrons, but holes, which are injected in n-type region. So here at the edge, their concentration is high. That's why we deal with Quasi-Fermi energy level for holes. But as they move further deeper in the n-type region, it comes back to thermal equilibrium because these excessive minority charge carriers, electrons, holes in n-type semiconductor, their concentration reduces, and we end up deeper in the neutral region with this thermal equilibrium condition. So that is the profile for Quasi-Fermi levels distribution. You can also consider this distance when all concentration of minority charge carriers injected vanishes as diffusion length. So we will definitely quantify this parameter. So that's distance along which injected minority charge carriers can travel inside the semiconductor before they fully recombine. So now we can look at this picture of band diagram together with charge carrier distribution. So we have neutral region of, so it's from like here, neutral region in p-type, which is characterized with very high concentration of holes and very low concentration of electrons as minority charge carriers. That is, concentration goes on this scale up. So here we have very high, here this dashed blue line is very low for minority charge carriers. When we inject electrons, which are plenty here in n-type semiconductor, into p-type, we have quite high concentration at the edge of the depletion region in the p-type semiconductor. And then, because of this compensation and recombination, their concentration drops, approaching concentration of equilibrium charge carrier, minority charge carriers in this p-type region, minority electron concentration. So similar happens here. So it all kind of shown already with Fermi energy level, but it's nice to reveal this in terms of concentration of charge carriers profile within the p-n junction. So it also goes from very high concentration of holes. We inject them into n-type region, and obviously next to the interface of this depletion region, their concentration is remain quite high. So then it compensated by majority electrons. These holes, injected holes, are compensated by majority electrons, and as a result, we end up with equilibrium concentration of minority holes in the n-type region. So that's what happens. And now, what is important to understand and quantify in order to get current voltage characteristic of a p-n junction? So actually what we need to know concentration here at this n minus WP, here in this region n WN, and also quantify the profile of minority charge carrier concentration distribution in P and N region. So means this profile of minority charge carrier distribution we should quantify, and that will be the key to understand the current voltage characteristics. So actually I want you to understand this, that in p-n junction the key information which defines current voltage characteristic and current voltage properties of this p-n junction is the distribution of minority charge carriers in p and n type region upon injection of charge carriers at forward bias, and we also will consider a bit more in details upon extraction of minority charge carriers from neutral regions when we apply reverse bias, because now we have only forward bias, so we inject charge carriers, we have higher concentration of minority charge carriers than thermal equilibrium. But if we apply reverse bias, you will see that it's actually opposite. We facilitate more drift current of minority charge carriers, and we will extract them from the neutral regions of p-n junction. Means that the concentration next to this depletion region with strong electric field will be smaller than equilibrium charge carrier concentration. But that will be a bit late. So now we have good understanding of processes in terms of band bending, Quasi-Fermi energy profile, level profile, and distribution, like quality understanding of charge carrier concentration distribution, specifically minority charge carrier, that's what matters, in N and P type regions of the p-n junction. So with this we can proceed further with quantitative analysis of current voltage characteristic, and the first thing what we need to do, we will try to derive equation for charge carrier distribution, minority charge carrier distribution when they diffuse in a p-n junction. So as you remember, we had similar procedure done when we considered diffusion of majority charge carriers in p-n junction. So you can recall this if you forgot. And there we derived this Maxwell relaxation time, how fast we can change concentration of majority charge carriers, and also this Debye length, the distance during along which the excessive charge carrier concentration of majority charge carriers decays by factor of E. So there, keep in mind, we considered both diffusion and drift, because we, as a result of this diffusion of majority charge carriers, we created some space charge which creates some internal electric field and facilitates also drift current. So we had drift and diffusion current. With minority charge carriers, that will be a bit different. So that will be later.
Sorry.
Yes.
Could you please elaborate on this again, like on this linear drops? I mean, in the depletion layer region. These, I mean, in terms of energy, you say this linear curves in the depletion region.
You mean here? This?
Yeah. Actually,
Okay.
These they are kind of quadratic, yeah, but.
So yeah, we just now for
simplify this.
because it's easier to show it. Usually, if you take a look, for instance, here at images from Z, physics of semiconductor devices, they also show for p-n junction these linear regions, because it's just easier to draw. You don't need to keep in mind how this quadratic function will change when you change potential. You keep it always flat, like not flat but linear, and what really matters is this shift here for forward and bias with the resultant potential barrier for charge carriers, and not really what is going on inside in terms of potential distribution, because in any way we have strong electric field, and charge carriers which are inside depletion region, they will be quite efficiently extracted from this depletion region. So they will not, it will not be such a big difference if we consider linear or quadratic distribution. But for some cases that could matter, but for understanding the current voltage characteristic and the key processes which are important when we apply forward or reverse bias, so we can easily use this linear distribution of potential.
The concentration of acceptors and donors in this region is kind of linear, yeah?
So that is a good question, because in depletion region, so it's by definition kind of so this strong electric field does not let charge carriers to stay there for long, so they don't establish any kind of equilibrium condition there, and we just, if some charge carriers appear in this depletion region, they are efficiently extracted. So that's why for being very from reliable side, we need to operate with concentration of charge carriers, majority and minority, in the neutral regions, because there we know that there is no strong electric field, and all these changes, what happens with concentration of charge carriers, they can be clearly described. With the concentration of charge carriers, you can get some effective concentration of charge carriers, which are in given moment of time in PN inside the depletion region of PN junction, but that's not corresponding to some real equilibrium condition, because they are, you need to inject them always in order to extract, so get some equilibrium concentration. But that's usually what not considered very much in PN junction specifically. So could be different story in PIN junctions or metal intrinsic semiconductor junction, because there we need to know concentration of charge carriers inside. But here, so there will be some gradient of concentration, obviously, because if you look at this Quasi-Fermi energy level position, so you see that this distance between Quasi-Fermi energy and respective bands, it changes. So obviously there will be some gradient, and that is because they meet with each other once they injected. Not all charge carriers which are injected in the depletion region can be extracted or like can be actually injected in the neutral region. So let's say electrons from neutral region of N-type are injected in the P-type, and the opposite happens for holes from P-type which are injected in N-type. They move in opposite directions within this depletion region. They meet and recombine. That results in the reduction of their concentration. So we have quite a complex dynamic situation when we add charge carriers, they transport there, distribute, and they also recombine. So there will be some profile of charge carrier concentration, and specifically if you want to calculate current voltage characteristic for the case of dominant charge transport, which is recombination via deep energy level within the depletion region, then it's necessary to know to calculate this profile of charge carrier concentration inside the depletion region. We will talk about this a little bit when we have already discussed ideality coefficient of current voltage characteristic, but definitely it goes beyond the scope which we are going to consider in this course. So now we can go for our slides and start to consider quantitative analysis of diffusion of minority charge carriers. So let us consider a semiconductor and one half of this semiconductor will be illuminated. So this will cause uniform generation of charge carriers within the volume. So we consider some P-type semiconductor, so we have P naught equilibrium hole concentration in this darkened region of the PN junction, and in this semiconductor sample. It's not a p-n junction. And in the left side we have P naught plus delta P, some non-equilibrium charge carriers, and also delta N. So we don't write here N naught plus delta N because N naught is very small, it's p-type semiconductor, so we assume that N naught is much smaller than delta N. Also, we consider not high level of excitation, means that delta P is much smaller than P naught. So it doesn't make a big difference for majority charge carriers in terms of hole concentration. But it does for minority charge carriers. So we increase significantly concentration of minority charge carriers. So if we have significantly higher concentration of minority charge carriers, then these minority charge carriers will start to diffuse. So let us consider uniform concentration of these electrons, delta N, in the illuminated area of the sample, because we consider that it's uniformly distributed all over the thickness of the sample, which is under illumination. And then there will be some profile how these minority charge carriers diffuse into the neutral region of this sample. Means region which is not under illumination. So our goal is to understand what will be this profile of minority charge carriers distribution in the dark part of the semiconductor. So we assume few things, that recombination lifetime for these minority charge carriers or electrons in this sample will be tau n. Tau n, I mentioned you that it's somewhere on average, it of course changes, but somewhere it can be, let's say the minimum values can be 10 to minus 6, which are commonly used. Let's say 10 to minus 6 seconds. Then we see that this recombination lifetime means how long this diffused minority charge carriers, non-equilibrium minority charge carriers, can live in this part of the dark semiconductor. This will be much longer than so-called parameter as tau m, which is Maxwell relaxation time. And that we have shown previously that somewhere in the range of 10 to minus 9 seconds. So 3 orders of magnitude, you can consider that tau m is much much smaller than tau n. Recombination lifetime of electrons in this semiconductor. So what does it mean? When we have some excessive, these minority charge carriers, like here in this region, their electric charge will be compensated very quickly, because tau m, Maxwell relaxation time, shows how fast majority charge carriers can respond to any change of electric charge in the material. So if we inject minority charge carriers electrons, it's some negative electric charge here, as it diffuses deeper, then immediately, but within this recombination, Maxwell relaxation time, it will be compensated by majority holes, and we will not have any space charge in this dark part of the semiconductor. that is different from diffusion of majority charge carriers, which I mentioned before, because we discussed with majority charge carriers they diffuse, but there is nothing to compensate their charge in this manner as it happens in the case of diffusion of minority charge carriers, because we have plenty of majority holes which can, within very short interval of time, compensate charge of electrons. So that means we don't have space charge, means we don't have electric field. If we don't have electric field, we don't have diffusion. We don't have drift of charge carriers. We have only diffusion. So that makes our life kind of a bit easier, because we can operate only with diffusion process. So in this case, continuity equation for electrons can be written as follows. So it will be 1 over q times djn, which stands for density of current of electrons, over dx minus delta n over tau n. And that should be equal to 0 under steady state conditions.
Why is the tau and current density 0?
It's a bit confusing.
It is a bit confusing. Let's make it a bit fatter and larger. Yeah. So that is our continuity equation, which we also discussed in details previously in general. So now we know that our current J, big one, and is caused by diffusion, only by diffusion of electrons. That will stand for Q times dN times first derivative of this excessive electrons concentration as a function of position along axis x over dx. So now we can substitute this expression here in the continuity equation and get the final, after some rearrangement, get the final differential equation, which will help us to get the concentration of minority charge carriers profile in the dark region of this semiconductor. So that will be, so we need to take first derivative of this expression over position. So it will be d squared delta n as a function of x divided by dx squared and minus delta n x divided by dn tau n. That will be equal to 0. So you see now it's easier, we don't have j anymore, so we can focus only on tau. So we just rearrange it a little bit, so get second derivative without any coefficient, and all coefficients we put, like constants which are involved, we put next to delta n as a function of x. So now we can introduce one new parameter, which will be Ln. This is called diffusion length of minority charge carriers, that parameter which I told you, along which the Quasi-Fermi level is still different from equilibrium Fermi level, so along which we still have this excitation condition because of injection of minority charge carriers. So that is diffusion coefficient of electrons times recombination lifetime of electrons. So Ln is diffusion length of minority electrons in this p-type semiconductor. So now with this we can write final expression for our differential equation, d squared times delta n as a function of x divided by dx squared minus delta n x divided by ln squared, and that will be equal to 0. So now we need boundary conditions. So which will be our boundary conditions? At position x equal 0 means like here at the interface between illuminated and darkened part of semiconductor, we will have maximum concentration of minority charge carriers, and that will stand for delta n at 0 x. So we will write here that delta n as a function of x at x equals 0 will be delta n at 0. Then at x equal infinity, obviously these minority charge carriers will not reach infinity, they will recombine before. So we can write that delta n x at this infinity position will be equal to 0. So these are our boundary conditions and our differential equation. This is second order linear differential equation. For the way how we solve it, we set up the so-called characteristic equation. So characteristic equation for this will be lambda square minus 1 over ln square, and that is equal to 0. So this is our characteristic equation, and we need to solve this. It's actually a quadratic equation. We need to solve it. So how do we solve it? We have discriminant, which is b square minus 4ac if we consider this with its coefficients a, b, c, and that will be 4 divided by ln squared. Now solutions for this characteristic equation 1 and 2 will be, in general case, it's minus b plus minus square root of the discriminant divided by 2a. So we can substitute these values. It will be 0 plus minus 2 divided by ln and divided by 2. So eventually it will be plus minus 1 over ln. So when we have two real and equal to each other, which is difference only in the sign, equal by magnitude, solutions for characteristic equation, the general form for solution of this differential equation will look like this. So delta n as a function of x is equal to c1, some constant, times exponent lambda 1 times x plus c2 times exponent lambda 2 times x. So now let us substitute instead of these solutions for characteristic equation what we actually got, and it will be delta n as a function of x equal to c1 times exponent x divided by ln and plus c2 exponent minus x ln. So this is general solution of our differential equation, but we need to determine this constant c1 and c2. So we know that for x equal to 0, delta n is equal to delta n naught, and x equal to infinity, delta n is equal to 0. So now let us substitute first 0, So it will be delta n naught equal to, if we substitute instead of 0 here for x and here for x, so it will be exponent of 0, it will be unity. So it will be C1 plus C2. Doesn't help us much so far, but now let us consider what will be at x equal to infinity. So the left side will be 0, we know from this boundary condition. And here we will have C1 times exponent. Let's keep this infinity here times ln plus C2 times exponent minus infinity divided by ln. So this will approach 0 because it's minus infinity, obviously very approaching 0. So in order to have 0 from the left side, we need this constant C1 also to be equal to 0, because this exponent is not equal to 0, it's approaching to infinity. So we need to get 0 in the left side, so that's the only option to have this 0 is to consider that C1 is equal to 0. So we already know one constant, C1 is equal to 0, and now we can, taking this into account and substituting it here, we can write that C2 is equal to delta n at 0x. So we got our constants and the general solution, like, let's say not general, the solution of our specific case, taking into account these boundary conditions, which we have, will be delta n as a function of x equal to delta n at 0x times exponent minus x divided by ln. So that is the function which gives us the profile of diffusing minority charge carriers in n-type, in p-type semiconductor. So if we come here again, so that is this like function which describes this profile. So we start from delta n at 0, and then according to our analytical derivation of this equation, it exponentially decays in the region of the, like, dark region of the semiconductor, and we operate with this parameter ln, which is diffusion length of minority charge carriers in this semiconductor. So from here we can easily determine like some physical meaning of this diffusion length. If we substitute instead of x ln, so it will be exponent minus 1. So at concentration of excessive minority charge carriers at distance ln from the boundary between light, illuminated, and dark part of semiconductor, will be delta n naught divided by Euler's number E. So that is the distance along which the concentration of minority charge carriers reduces by a factor of E. So now when we keep in mind this profile distribution, which is very important in the derivation of current voltage characteristic of p-n junction, because I mentioned you that the key feature which defines current voltage characteristic is actually distribution of these injected minority charge carriers in the respective regions of the p-n junction. So we can proceed further and define certain conditions in the framework of which we will further derive equations for current voltage characteristic of a p-n junction. So how much time is left?
15 years.
Okay, so probably we have enough time to define them. So first of all, we consider one-dimensional model. So let's put here one-dimensional model means that current transfer along the cross-section of p-n junction is uniform. It doesn't change from position to position, and that's why we deal with only one dimension, like this coordinate x. The current which flows through the p-n junction should be small. So that will allow us to neglect with voltage drops over neutral regions and contacts. So that's another factor which should be considered. We have ideal ohmic contacts. But even with ideal ohmic contacts, as I mentioned before, when we considered the measurement of depletion layer capacitance, neutral region of semiconductor, nevertheless, it's quite doped, heavily doped, and very conductive because of high concentration of majority charge carriers. We still need to consider that it possesses some electrical resistance. So, so in order to have minimum impact of this electrical resistance on potential applied external bias distribution, we need to consider that electric current which are going through the p-n junction are not high. And in this case, we can claim that all external bias which is applied to p-n junction will, this potential difference will drop over exclusively depletion region, not any other parts of the p-n junction. So everything what we apply is actually dropped over p-n junction. So ohmic contacts we mentioned. Obviously, if they are not ohmic, that they will possess high resistance and applied bias will split in different components, which we don't want. We want also small level of injection of minority charge carrier. In these semiconductors, we don't want to have the case when we inject so much minority charge carriers that they actually exceed already next to the edge of p-n junction majority charge carrier concentration. So they should remain minority charge carriers. And that actually partially connected with the small currents, because if we keep small currents, we keep small level of injection. But it's good to specify it separately. So small level of injection.
So what will be if this minority carriers will exceed so
yeah, then it will be already. So first of all, it will be already open p-n junction. So we will not consider this anymore as a p-n junction, because it will behave just as a resistor with small resistance. So in that case, all this p-n junction theory doesn't make sense, because external electric field compensates in this built-in field inside semiconductor completely. So we don't have this electric field non-uniformity inside the p-n junction, and potential barrier is 0. So then we inject so much that all this doesn't make any sense anymore. So we can just burn this p-n junction, like what was p-n junction before. So also we don't need any surface effects. So we mentioned about surface recombination. We don't want to have them in order to have this to derive ideal current voltage characteristic. So no surface recombination. And there are no generation recombination processes in the non-equilibrium of non-equilibrium charge carriers inside the depletion layer. So that is something what we partially considered answering like your question. I mentioned that if you have recombination via some trap, deep trap, in the depletion layer, then we need to know concentration profile of charge carriers in the depletion region in order to know how they will like recombine via this deep trap. And when we derive now this ideal current voltage characteristic, we assume that there are no either generation via these deep traps or recombination processes within the depletion layer. So we assume that electric field is so strong that it just immediately extracts all charge carriers from there. So nothing is going on. So later, this ideal current voltage characteristic can be modified by introducing such parameters as a non-ideality factor. I believe did you determine this non-ideality factor in labs or not? I guess it was not involved there, which is a bit pity, but it's one of the parameters which shows how much current voltage characteristic of a device deviates from real, like this ideal current voltage characteristic, which we would assume considering only pure diffusion charge transport without any contribution from generation recombination. So we can write here no generation recombination processes in the depletion region. So these are the conditions which we need to consider when we deal with the derivation of a p-n junction. And as I mentioned before, we can maybe where we can do it, they close, yes. So let me again show you our slide. Yes, this one. As we mentioned before, we are interested in two parameters. First, that's this profile of minority charge carrier distribution. So we already learned something about it because we considered this specific case of minority charge carriers diffusion from illuminated to dark part of p-type semiconductor, assuming low level of excitation. And also we need to start with this so-called, we used in our derivations this term n delta n at position 0. So far we don't know what will be this delta n at position 0. We just say that, okay, at position 0 there will be some concentration of minority charge carriers. But in order to proceed further, we need to know what will be this concentration here. And afterwards we can combine this information about concentration of minority charge carriers at the edges at 0 position and with the profile which we derived, and eventually come to the point when we get the expression for current voltage characteristic. So I believe at this point we finish our today's discussion, because it would be better if we start from scratch next time and finish it in one approach. Okay, if you have any questions, you're welcome.